Hi friends, this is an interesting interview question related to programming, specifically numerical programming, that is very popular at FAANG companies. Again, the FAANG companies themselves don't have Microsoft, so I have added an M here. And this question is often considered as an easy to medium question, again, depending on the role. And you could encounter this programming question, especially for data scientist roles, or machine learning engineer roles, or software development engineer with machine learning roles, or even for applied scientist roles. So if you're looking at it from a data scientist role, this question will be considered as a medium level hardness problem. If you're looking at it as an applied scientist or a machine learning engineer type of role, or a software development engineer for machine learning role, it will be considered somewhere between easy and medium, right? Again, a variation of this question or small twist on this question has been asked in almost every major FAANG company. And it's also very popular with good product-based startups. Okay, so with all that, let's go into the question itself. So for this question, you have to write code in any language of your choice. For most data science and machine learning roles, you tend to write it in Python. So the question is as follows. Given an integer n, return true if n is a perfect square, else return false. For example, if n is 16, because 16 is a perfect square, because 16 can be written as 4 square and 4 itself is an integer, so we return true. On the other hand, the square root of 18 is not exactly an integer, and hence we return false. That's what is the definition of what a perfect square is. Again, while solving this question, please note that you cannot use inbuilt functions like what we have in math module, right? Like sqrt, because if you're explicitly computing square root, this problem becomes trivial then, right? So please make sure that you try to attempt this question without using inbuilt functions like computing the square root. Okay, cool. Again, the objective that we have for this specific sort of problems is not just to tell you the solution, but to help you improve your thought process. That's very, very important, because if you have the right problem solving skills, again, our objective here is to help you build the problem solving skill. Because if you have the problem solving skill, given other problems that you have never seen, you can still tackle them. And the problem solving skills do obviously start from your conceptual clarity. So an interview question like this is trying to see if you know coding, if you have core conceptual clarity of basic mathematics, which is very fundamental to most of machine learning and data science. And equally importantly, can you work out a solution? And when you're trying to think of a solution, try to map this problem to techniques that you already know, or to other sorts of problems that you might have already solved in data science, machine learning, in general mathematics, right? Again, while designing the solution, please use simple examples like n equals to 16 and think about it. Similarly, n equals to 18. Whenever you're designing a solution, using examples is a great strategy, and also mapping it to techniques and problems that you have already solved is a good strategy for you to arrive at a solution fast and in a very systematic fashion. Again, our objective here is not to just tell you the solution, it is to help you build the thought process and the problem solving skill itself. Cool. So again, before you see the solution, I will explain the solution a little later in this video, but please try to give it 2 to 3 attempts before viewing the solution. Because a lot of students, we see this, they see a problem, they try to solve the problem for 5-10 minutes, they directly go to the solution. By seeing solutions, you will not build your problem solving skills. It is the struggle, it is your mental struggle that you go through when you try to tackle the problem from multiple ways. That mental struggle, right? That fight in your head, right? That's what will build your problem solving skills. Seeing solutions will never build problem solving skills, which is extremely important if you want to join a FAANG company. So a lot of our students ask us that, hey, I want to end up at a top company like a FAANG company. What should I do? In addition to all the conceptual clarity, mathematics, everything, problem solving skills are important. That's what we try to build even through our course assignments. Again, when I say 2 to 3 attempts, try to attempt to solve the problem right away. Right away, try to solve the problem, which is n. After a few hours, suppose you failed to solve the problem, give it a few hours of time. Let the problem brew in your head. Let it sink through in your head. After a few hours, again try it. Worst case, after even 1 day, give it a shot. So give it 2 to 3 attempts before you check out the solution. That's very, very important, because without that struggle, you will never be able to build the problem solving skills. And once you build the problem solving skills, it doesn't matter how hard or how medium or easy the question is, you'll still be able to solve it because you have the core solving skills themselves. Cool. Again, if you could not solve this question even after multiple attempts, you can always check out the solution. And after you check out the solution, ask yourself, try to debug yourself, your own thought process. Try to ask yourself, what gaps do you have? Do you have a conceptual clarity? Is it that you don't know a technique which is very important? That's called a conceptual clarity gap. Or you are not able to map, which means you need more practice. So try to debug why you are not able to solve it after giving it some time. Now please pause this video because I'm going to go into the solution. Again, please give it a good at least 2 to 3 attempts before you check out the solution, because that's what matters at the end. It's not the solution, it is your approach to the solution that matters. Okay, so while solving it, I'll think like a beginner, right? So in machine learning, whenever you learn programming, basic data structures, basic algorithms, again, which are all fun, basic data structures and algorithms are fundamental even to machine learning and data science, right? You learn about simple concepts like iteration, recursion, if-else conditions, all of this stuff. So try to see which of these techniques that you already know you can employ to solve this problem, right? For example, imagine the n that is given to us is 16. Always work out examples because that will give you a clarity of thought. Now, if n is 16, we know that if there exists a square root, right? Imagine if square root of 16, we know it is 4, it is an integer, and hence 16 is a perfect square. Our objective is to compute a square root or a number very close to the square root. Now we know the square root has to be less than n itself. So what I'll do here is from 1 up to n, let us try to, again, this method is very simple. We are simply using iteration here. We are simply using iteration. We start with n equals to 1 and we say, hey, if n equals to 1 is 1 square. So let's compute 1 square, which is 1. Is 1 equals to n? No. So, or instead of saying n equals to 1 here, sorry, let me just say iterator, I equals to 1, I'm sorry. So from I equals to 1 to n, I'll keep iterating. What am I using here? I'm using a very popular, very simple technique in programming and solving such problems, which is iteration, just a simple loop. So I try I equals to 1, I check I square, which is 1. Is 1 equals to 16? No. Then I try with 2, 4 not equals to 16, 9 not equals to 16. 4 square 16 exactly equals to 16. Then I will say yes, because 4 square, because I'm only checking integers here, because 4 square equals to 16, which is equals to n, I will return true. Very simple method, right? Now imagine, so suppose if my number is 18, let's assume my number is 18, right? Then I search, okay, 4 square is 16, then I try 5. What is 5 square? 5 square is 25. So I realized that from a number which is less than my 18, I've gone to a number greater than 18 by just a single increment, which means the square root of 18 will lie between 4 and 5, which means it will not be an integer, so I will return false. A very simple mechanism. So what are we doing here? If you think about it, we are writing a simple iterative loop with some simple if-else conditions added to it. Again, this is not a wrong solution. This is the simplest solution to tackle it. Many of you might have thought of this simple iterative solution. Now, if you think about it, this whole iterative solution is like linear search. Again, linear search is something that we describe in our course videos in a lot of detail. And this is something which is very basic that most data scientists are expected to know. It's called linear search because you're searching in a linear fashion, one after the other, right? That's what you're trying to do here, right? To see if you can find an integer whose square is exactly equals to 16. And if you can't find it, imagine if n equals to 18. And you can't find it because 5 square is 25. You can't find, you have 16, then 25. There is no 18. You just return false. So what you're doing here is a simple linear search, right? Very simple. Again, you're using iteration as a strategy, but this problem is very, very similar to a simple linear search. And what is the time complexity of linear search? It is order of n. Very simple again, right? So the time complexity of this solution is order of n. Now comes the more interesting question. Again, always try to map the algorithms or any problem that you have into algorithms that you already know, like linear search. Now, the moment you map this problem to a simple linear search or an iteration-based scheme, obviously you also know binary search. Again, this is something that we cover in our course videos along with its time complexity, right? The moment you know binary search, the moment you think of linear search, obviously the next thing, because linear search has an order of n time complexity, you know binary search has order of log n, you should say, hey, can I use binary search here? Now let's try to see if binary search can be applied here. Again, all that we are doing here is we are mapping the problem that we have into techniques and algorithms that we already know, like linear search, binary search, etc. Right? Nothing very fancy. That's why this problem is in the easy to medium scale. Cool. Now let's work out. Again, let's assume n equals to 16. Right? So I'll have my, let's assume, how do you do binary search? You have a lower index or the left index and you have a right index. Right? Simple. And you keep halving it. So first and foremost, I'll half it. I'll say, hey, what is 8 square? 8 square is 64, which is greater than 16. Which means if 16 was a perfect square, the square root of it will lie in this region. So I don't have to worry about this region on my number line. Again, what you have here is a number line, right? From 1 to 16, all the numbers. So you don't have to worry about this region. You don't have to worry about these numbers. Then what do you get? Then you again half it. You get 4. 4 square is 16. Oh, you exactly got the answer that you're looking for, and you say, hey, 16 is a perfect square, and return true. Again, what is binary search? Binary search is given an array or given anything, you break it into halves. You say, hey, does the solution lie in this half or does the solution lie in this half? If the solution lies in this half, then you break it again and ask the same question recursively. Does the answer lie here? Does the answer lie here? Very simple, right? Now, again, take a slightly more tricky example. Imagine if n equals to 18, right? Your left will be 1, your right will be obviously 18 first, and then you keep halving it. Once you half it once, you get 1 to 9, right? Again, depending on how you implement binary search itself with your floors and seals and stuff like that, right? So basically what you're doing here is 1 to 18, you'll first half it into 1 to 9, right? Which you'll again further half it into 1 to 5, right? Because you know that this square root has to lie in this. And you keep halving it. At some point, you'll recognize that there is this number 16. Because 4 square is 16, which is less than 18, and you have 25, which is greater than 18, and hence 18 cannot be a perfect square itself. You have to just slightly modify binary search carefully. Again, the logic itself is binary search. That is simple. But very often when students end up writing or interviewees end up writing code for this, they make so many mistakes. There is a very interesting statistic that almost 70% of candidates who interview at FAANG companies cannot even implement binary search perfectly without any bugs. I think I've heard these statistics from some of my software engineers earlier. Right? I think 60 to 70% of them cannot implement even binary search. 60 to 70% of interviewees at FAANG companies cannot even implement binary search without bugs. So you have to be very, very careful to handle all boundary cases and things like that. Cool. Again, here eventually you'll reach a stage where your left index and right index are 4, and which is not equals to square root of 18. So you return false. Right? Simple, because 4 square 16 is not equals to 18 and you'll return false. Simple logic, right? Now, remember here that since we are using binary search, we just have to modify it slightly to our needs, but you can always try out more examples like n equals to 36, n equals to 41. Just play around with it to get the logic, to get the boundary cases correctly. And we know binary search has a time complexity of order of log n. And we can implement binary search either recursively or iteratively. Obviously, iteration is better because it doesn't have the runtime stack. Right? So simple logic. So we'll try to implement it iteratively, carefully. There may be some mistakes, but we'll try to debug them using simple test cases. Cool. Now, whenever you're writing code, please remember that you should always handle the boundary cases carefully. What if n is not a positive integer? That's very important. If n equals to -1, what happens? If n equals to 1.2, what happens? So all these boundary cases you should always handle. Let's try to write iterative code. Let's write a lot of test cases to see that all the boundary cases are gracefully handled and there are no bugs in the code. This is very, very important. Simple test cases can be what if n equals to 0? It should be true. What if n equals to 1? That's also a boundary case when you're doing binary search, right? And similarly, what if n equals to -1? Like, let's try to write a bunch of test cases and run it through the code that you write, or at least just check if your code can handle all these boundary cases or test cases gracefully. Of course, you'll search for n equals to 16, n equals to 18 and examples like that, obviously. Okay, so here is a code. Again, whenever you write code, please try to add these simple comments. So this is a function which is perfect square n, right? Check if n is not an integer. How do I check if n is not an integer? If int of n is not equals to n, right? Because imagine if n is 1.2, then int of n will be 1. Then 1 is not equals to 1.2, it will return, right? If it is not equal, it will return true, so you return false. You say, hey, what I have is not an integer, so this problem doesn't make sense. Similarly, if n is less than 0, return false. Right? Very simple. Then again, these are two simple boundary cases that we are handling. Then here is your simple, again, this whole thing is simply your binary search slightly modified. This is your left index, this is your right index. Again, we have taken L equals to 0 because what if N equals to 0? We should be able to handle this case also. That's why we've taken the left as 0, right as 1. Again, we should also handle N equals to 1. Because if N equals to 0, we should return true. If N equals to 1, we should obviously return true. So to handle these boundary cases, because we have these in our test cases, we changed 0. Initially, I think I wrote L as 1. Because that's what I'm used to. But then I realized that it is failing if N equals to 0. Right? This code wasn't working if I give N equals to 0. So then I changed it slightly. So having this bunch of simple, nice boundary cases and test cases will help you debug your code and get it better. The rest of this logic is fairly straightforward. This is a standard loop. This is your standard iteration, right? Where you break it into two halves. Your left index should be less than or equal to right index. This is your middle index. Middle index is you take the center point, right? You take the center point in your left and right indices. Then you check if m square is greater than n, then you change the right. So simple logic, right? Okay, this is your left, this is your right, this is your middle. If your m square, remember, if your m square is less than n, right? Look at this. If m square is less than n, then what happens? Then your L has to, then you change your L here. Simple. If your m square is greater than n, you change your right index now to m minus 1. That's it. Again, you're just halving it. Whatever logic you already know in binary search, you're just implementing it carefully. And at any point, remember, if you found an m where m square equals to n, you have to handle that case, right? That's why you have this if, elif, else. This else will work only if m square equals to n. If you find such an m, you just return true. If you don't find it at the end of this whole loop, you just return false. Again, there are many correct ways of implementing binary search carefully. But just make sure you're writing all the test cases carefully and working them out. Okay, so these are some of the test cases that I've written, right? Fairly decent set of test cases. What if n equals to 1? What if n equals to 16? What if n equals to 0? What if n equals to 18? What if n equals to minus 1? What if n equals to 35? So these test cases, if there were any bugs, when I first wrote this code, I wrote a small bug here. I said L equals to 1. But then I quickly realized that that was failing if I give n equals to 0. Then I quickly changed my code and tested it through all the test cases. Very simple. Just be careful when you write your test cases to cover all the scenarios, right? Very simple case. Now, there is an alternative way of solving this problem also. Completely machine learning way of solving this problem. Till now, what we have solved is basic data structures algorithms, right? Basic linear search, binary search stuff, right? So while this is great, there is a completely different machine learning way of solving it. Because what we want to find is, we want to find an x such that x square equals to n. Now, how do I write it as an optimization problem? Now, if I try to write it as a loss, I want to find an x such that x square minus n, right? The absolute value of it, or the squared value of this, is as small as possible. Because this squared value will always be positive. The minimum value will be 0. And when it is 0, I know that x is nothing but the square root of n. Right? If you think about it, right? So I can pose this as an optimization problem and say, hey, I want to find an x star such that it minimizes x squared minus n whole squared. And when I have an optimization problem like this, I can simply use gradient descent or stochastic gradient descent. Right? I don't have stochastic gradient descent here. I can directly use gradient descent itself. Very simple. Now, at the end of the day, you will find some x star which minimizes this. Now, if x star is an integer, or it's very, very close to an integer, then you say, like for example, if your n is 16, you might get your x star as 4.00001. Something very small like this. If it is very close to an integer, or you might get x star equals to 3.999999. So just check that. Just try to find the integer closest to this. And if that integer square equals to your n, then it's a perfect square, or else it's not. Because remember, your gradient descent does not do it only on integers. It finds some real value x. Imagine in this, your x can belong to any real value when you're solving the optimization problem, right? So whatever answer you get after a bunch of iterations of gradient descent, you're done. This is one approach of solving it. Now, in this case, if you try to plot this function, okay, I've taken n equals to 16 here. I've taken n equals to 16 and I tried to plot this curve. Because if you think about it, there is x square here and there is a whole square here. So this becomes a power 4 polynomial. If you try to plot this curve, it looks like this. So when you have a plot like this, you should take your first x0 when you're doing gradient descent, right? You have your initial value of x, which is called often as x0. Try to take it as a positive value. You can take x0 itself as plus n. This is one possibility. If you take it as plus 1, what happens? Then your x0, so 16 will be somewhere here. Then you'll keep doing gradient descent and you'll arrive at this point plus 4 because you don't care about minus 4. Right? Because you want to arrive at this point in your gradient descent. Again, this whole curve itself is fairly complex, but if you start your gradient descent from this point, then you'll keep moving towards this minima here, not this minima. Again, even if you arrive at this minima, that's okay, because if your n is a perfect square, you'll have plus 4 here or minus 4. Whatever you get, your answer can still be valid, right? Again, you can tweak around the gradient descent to just make it work for this specific case. And this is a completely different way of tackling. I've seen some interviewees tackle this question from this angle also, which is perfectly valid. Again, getting a time complexity on it is slightly complex because gradient, you have to talk about gradient descents, convergence rate and problems like that, right? But in general, this is also a pretty good strategy because you're applying something in data science and machine learning to solve the problem at hand.